The second case in which the dose is higher than Km, when the concentration is higher than Km, okay. If we go back to Michaelis-Menten equation, it will be Vmax multiplied to the concentration of the drug. Okay, if the concentration of the drug is higher than Km, then we can ignore this. This will go with this. Then the rate will be equal to Vmax, which is constant for the same drug. When the rate is equal to constant, then the kinetic of the drug is behaving as zero order kinetic. Okay, and that's what you will have on the profile after that, telling you the regions of each of those on the profile, in which this called zero order region, because the drug is behaving as zero order, first order region, because the drug is behaving as first order, and we have in between what we call it Michaelis-Menten region, or the mixed any of the names that we have here, Michaelis-Menten or saturation region, capacity limited or mixed order region. Okay, but usually Michaelis-Menten region. Okay, but just be careful that we are drawing rate versus the dose or concentration of the drug. What if for IV bolus single dose, okay, we are drawing concentration versus time? Before, when we had concentration versus time, not rate versus concentration versus time for a single dose, we had this, okay, and when we were changing it to semilog, let's say, concentration versus time, we had this, right? So by default, we said that this will be linear kinetic. Okay, when we had if you have concentration versus time, but it's like this, but when you change it to, and same thing, by the way, either we are talking about semilog or len or log, same kind of things. Any transformation will result in similar kind of thing. Rather than have linear kinetic as you already know, you will have something like this, okay, and that's will tell you by default that you don't have linear kinetic because you lost your linearity. That's why one of the first things that we said when we have the introduction about changing the profile from rectilinear to other profiles, that you can have some idea about the kinetic or the order of your reaction. Okay, if we go back to the concentration that we have versus time for on rectilinear profile of non-linear kinetic, again we said we will have it like this, which is similar, same as I have here, similar to whatever you know for first order or linear kinetic, but you can't have it, visualize it, and when you have it on rectilinear profile. But let's talk about the region or regions of the profile or the diagram that you have according to whatever we said here. We have zero, we have first, and we have Michaelis-Menten. We said at low concentration we have what? First order kinetic. So this will be first order kinetic. Okay, at high concentration we will have it as zero order kinetics. Okay, and the middle we will have it mixed or Michaelis-Menten region. Okay, when you change it to let's say semilog profile, again the regions the location of each one of those regions will be the same. It won't be different. But once you have it like this, you will have it at low concentration, right? It's behaving, as we said, as first order, which is linear. So it will be behaving as first order. At um, higher concentration, we will have it at zero order, and the middle, we will have it as mixed or Michaelis-Menten. Okay, one of the profile that can give you some idea, and just remember what we will have, what we are having here is concentration versus time, rather than this diagram for Michaelis-Menten, which is rate versus concentration. Okay, you have this on your slide, in which we have plasma level or concentration versus time. We have this profile, and we have this profile, and we have this profile. Okay, this is C, this is A, this is B. If we consider C as a profile of drug number 1, that we know that it's linear kinetic, and A and B are for drug number 2, that we don't know the details of their kinetic. You can tell from the profile, and again this is on Semilog for sure, because you have a linear profile for the linear kinetic drug. Okay, from whatever that you see here, if we have those two profiles for the same drug, you can tell that at low concentration, okay, or at low dose, the drug is behaving as non-linear. Okay, when you increase the concentration, the drug is behaving as non-linear. So you will see the non-linearity when you are increasing the concentration. Okay, but again, when the concentration is becoming lower, again the drug is behaving again as first order or linear kinetic. And as I mentioned in the beginning of this chapter, that if the drug under therapeutic window is behaving as linear, which means if the drug under therapeutic window is giving me this profile, I don't care if increasing the concentration will give me nonlinear kinetic, because it's easier for us to deal with linear kinetic. So if it's under therapeutic window is linear, so I don't care about nonlinear. But when the therapeutic window having nonlinear kinetic, then you will deal with nonlinear kinetic. Okay, and the same thing for when you have area under the curve, as I mentioned earlier, and the same thing for steady state concentration versus dose of the drug. If we are talking about, you have C drug with linear kinetic, so whatever increasing the dose, the drug is still behaving as linear because it's proportional. Okay, but when you have nonlinear kinetic, you will have this profile. Okay, so this is for a drug which is non-linear kinetic. At low dose, the drug is behaving as first order. At higher doses, the drug is behaving as non-linear. Okay, then you have tables in which I'm just reminding you about the drug, if it's following first order kinetic or zero order kinetic, which those kind of things you know already, but just to remind you, when we have zero order versus first order, despite the fact of whatever we mentioned earlier, when you have first order, then the amount of the drug eliminated per unit of time is changing with time. Okay, this is changing, and as time increases, it's decreasing. If you remember when we were talking about amount eliminated per unit of time, but the fraction of the drug eliminated over time will be constant. Okay, so how much is the fraction of the drug eliminated per unit of time will be constant, and it's the same 0.12 each time in the example that you have. Try to have it or calculate it, and you will have the same numbers. And I just mentioned in a sentence I have it as a sentence under the table that the amount of the drug eliminated may change with the amount of the drug in the body. The fraction or percentage of the drug eliminated over a given time remains constant. Okay, but when we have zero order kinetic, then the amount of the drug eliminated per unit of time is constant, which is related to the rate. Okay, but the fraction eliminated is changing with time, and it's usually increasing. Okay, and this is what you already know from before. Okay, but in between zero order and first order, the drug is behaving in a mixed way that we can't define if the drug is first order or zero order, which is this region. Zero order, we know that the drug for the rate of, let's say, rate of elimination is constant per unit or per dose or per concentration of the drug, but here is proportionally related. In between, you can't define it if it's first or zero or it's behaving an exact way. That's why we call it a mixed region, which is something in between, or a Michaelis-Menten equation. Okay. To estimate the Michaelis-Menten parameter, we need to determine the parameter of Michaelis-Menten. We have Vmax and we have Km. And to determine them, we need to use, we have so many models for the Michaelis-Menten equation and determination, depending on the scientist that or the reference that you are using. We will or you will have things for a single dose, and you have the things for multiple doses. Okay, and the models that will be explained is the easiest that you can find in your reference. Okay.